And our next speaker is Dr. Shawn Gao, whose topic is the pseudodynamic hypersimulation techniques. For some reason, the hypersimulation technology experts at MTS are all named after Shawn. I don't know why, but it's not required if you are interested in the career opportunity at MTS. So Shawn is our senior system integration engineer at MTS, and he has a specialty in the integrated simulation and the testing techniques as well. His research interests are the structural dynamics and the structural control. And he has more than 20 journal and conference publications around the globe. And he conducts several system setup and technical training. And Dr. Gao received a PhD degree from Purdue University, and he's a licensed professional engineer in the United States. All right, Shawn.
Okay, thank you guys for the introduction, and thank you Shawn Yu and also other previous speakers who already explained a lot of the concepts and the techniques about hybrid simulation. So for some of you who may not be familiar with this concept, I think until this point maybe it saved me a lot of effort. So my presentation will be really easy. So basically, this presentation I will just kind of going into a little bit more details and tell some, talks about some techniques and tools which you need to conduct a successful hybrid simulation. So the organization of this talk, I'm going to basically go through from like a very base level, like the very base level 2, and go up to the hybrid simulation level, which Shawn already talked a lot anyways. And then finally, go into a little bit more broad view, bigger picture view, like the hybrid system essentially is a separate physical system. Some of our previous speakers already talked about. This is one of the key areas now around the whole world in terms of research and development. So then I'm going to talk, give some quick conclusions. So first thing I'm talking about is MTS calculation channel function, this technique. So Shawn Yu already mentioned a little bit about it, but I will give you a couple more examples. So in terms of regular PID control, whenever you talk about actuator control structure, structure control. So in the very base level, most of the systems are using a PID control, right? So then you have you can do either a load control or you can do a motion control, displacement feedback or force feedback, right? You have your command, you have your feedback, you close the loop based on that. So that's easy if it's only one channel, one single actuator. But for example, BOF control, if you have for example, 2 actuators now. You have a left one and the right one, and you are controlling this table, and this table needs to be controlled in the global degree of freedom, right? It's the axial and also the rotational degree of freedom. So what you really care about is the structure degree of freedom. And then what you can do is that you can use the MTS calculation channel function to set up some simple functions to do that coordinate transformation, right? Because you know that between this left and right actuator space and also the global structure space, you can set up that equations easily and convert it into the matrix formation. And then now you are able to do a BOF control, for example. Now your commands are all in the structure degree freedom, right? The translational and the rotational. And your feedback, of course, is still in the actuator space. So you need to go through some sort of transformation so that your feedback is also going to be in the global DOF, degree of freedom space. Then you can do this calculation and this kind of control. You can do either force or displacement control, right? So in terms of setting up, then MTS station builder, when you build a station, so what you do is that because this axial and moment, they are based on calculations, so you use a virtual output instead of real hardware resources. And this virtual output can be expressed in that calculation editor. So you basically write out the equation between your structure degree freedom and the actuator degree freedom, right? So what are the advantages of using this calculation function? First, this calculation editor in MPS software, it could involve operations on basically all the signals which go into your controller. It's not only every single actuator displacement or force, command, or like the servo valve driver, anything inside your controller, those signals can be manipulated and operated using this calculation channel function. And also, this code, when you write down the calculation equation, and this code will be downloaded into the controller, and that code can be executed in the controller in a real-time fashion, right? Saves you trouble because you don't need to go deep, like write down your C code. Then you can use the calculation editor to easily write down your equations. But if you are familiar, you are expert in C, then you can come up with some fancy calculations. You can do that, and then this code all be compiled into the controller to run it. So in terms of another application, a little bit more advanced application for this calculation editor, for example, this is the Newmark integration algorithm for hybrid simulation. For example, if you have a numerical substructure, you have some simple, let's say, a shear building, you have multiple degree freedom dynamic equation motion. You can write down your equation motion solver using this calculation editor functionality, and then your numerical substructure is all fully developed in the MPS controller, and then you can do hybrid simulation in that way. For example, this is in Encre. So this whole substructure, this superstructure, if you assume approximate using a reduced order model, then you can write down the Newmark solver for this superstructure. Then you can test those bearings, those physical bearings, because they are very nonlinear and they are difficult to model. And that's the purpose of hybrid simulation, right? You model anything you can model. It's easy to model. And then for the difficult to model part, you test them in a physical rig. So that's just one application for the calculation editor that you can do in terms of hybrid simulation. And also a lot of the digital signal processing functions, you can also do it in the calculation editor. For example, you can set up this finite impulse response filter, FRI filter. So, define your passband, stopband, all these good things, and then do the signal processing directly in the controller level. So, for example, that's like after you add this filter, then you can eliminate your system noise significantly, because a lot of times, especially when your signal is used to close the loop, then those noises sometimes can be a big trouble. So you can define some filters in there to help your testing, not only in terms of hybrid testing, also in terms of general, just conventional testing. You can do a lot of those in the calculation editor. So then the next tool I'm going to introduce a little more is the MPS DOF control tool. Shawn Gao already covered a little bit about that, give an introduction about that. So, for example, this is the Swinburne system. We already seen that. This is like an 8 actuator, controlling all 6 degree freedom, right? And then for this type of system, think about it, if you write down in a calculation editor, that effort becomes non-trivial. You need to, write down a lot of equations, and especially they are like over-constrained system because you have more actuators than the degree of freedom. and those equations need to consider all those constraints, so it becomes a non-trivial task. But using the DOF control tool, it's becoming much easier for the user to program in that. So this DOF control has been extensively used in a lot of our advanced systems, and it can be used in the displacement control, force control mode, and mix control mode, of course, and control any degree freedom. You know, if you have 3 actuators, let's see, controlling 3 degree freedom, also use that tool. You can build your DOF controller easily. And you can use some external transducers, not only the LVDT or the false transducer we provided to you. You can use some external transducer to close your loop as well. So, and this DOF control thing has been used in hybrid simulation more and more. And another, you know, this Shawn already mentioned in the University of Minnesota, they also have a similar mask system. And for example, you know, you can even couple multiple of these systems. Both of them are 6 DOF control, and you can, you know, set them up to make them moving synchronously. And if you are testing a long article, for example, this is a vehicle. Actually, this is a ground vehicle application. This is this system is longer than one can handle. Then you can couple 2 of those tables to do your testing. And this example, like a 6 DOF shape table, you know, they are all in different angles. Now think about that. If you write out your own equation, that becomes so all the large kinematic transformation, all those things, it's kind of you know, difficult to program by yourself. But in the DOF control tool, we give you all the you know, user interface. You just need to know, okay, where is my, in the spatially, where is my control point? Where are all the actuators? Their orientation, you define 2 nodes to define the single actuator. Then visually, you know, it gives you all those visualization, and you know, you can define them very easily. Again, just a tool to facilitate any user to do more advanced testing. And in the DOF control, you know, similarly, you know, what happens is your command is in the global structure degree freedom, and of course your feedback. First of all, they are all coming from individual actuators, and you have to go through some transformation, right, to transform from the local actuator degree freedom into the global structure degree freedom. Then they are now all in the structure space. Then you can do your control based on that. And also the force balance control is that you know, you also need to satisfy not only the motion, you have to satisfy the motion accuracy, but also for the mask system, you also maintain the force balance. Then that converges both displacement and force. So this is from Swinburne. You know, you already seen this. So DOF control coupled with hybrid simulation is being more and more used, becoming a very advanced testing system. Makes, you know, you can do more advanced hybrid simulation using those tools. And then, you know, go to the next level is like, okay, we have those tools. Now, you know, pseudo-dynamic hybrid simulation solution we offer. So, Shawn, you already covered this pretty much, but, you know, terminology-wise, we used to use quasi-static hybrid simulation all the time in MTS. Then I know Swinburne prefers pseudo-dynamic terminology, and I know some other universities, they prefer pseudo-dynamic hybrid simulation. The difference is that, so we treat them, you know, it's just slow hybrid simulation, right? Quasi-static wise, it's like in terms of testing, because if you only look at the testing article, it's like a static testing, really slow. Sometimes you cannot even see the motion just by your naked eye. But why we call it pseudo-dynamic? Because when you do hybrid simulation, your system is a dynamic system, because your numerical substructure has all the equation motion, you know, has all the mass, damping, and you know, inertia and damping terms. So you are solving a dynamic problem So your whole system is actually a dynamic analysis. So that's why we call it pseudo-dynamic, but in the meanwhile, sometimes we also call it quasi-static, but just a slow hybrid simulation. So Shawn, you already talked about this. UC Berkeley has this nice middleware, OpenFresco developed, and MTS has associated CCSI software. So OpenFresco is independent of any FEA software, right? One of the questions we had before was like OpenSys, how it compares with other commercially available FEA code. So what happens is that you don't necessarily need to use OpenSys. You can actually use ANSYS, Abacus, and for example, recently we also developed the interface for the multi-body dynamic software Adams. So Adams can be linked into the hybrid simulation world as well. So if you are more familiar with Abacus and ANSYS, yeah, you can use that to do your numerical substructure modeling and still use the OpenFresco as a middleware to interact with the testing hardware. So those solutions are all ready. So again, yeah, that's the middleware, the OpenFresco, and this is the CSI, which mapping the control channel. So same thing you already saw. So for example, this one I go a little bit more detail. This is the DTU project. They are testing this blade, Denmark Technical University, and we had a couple, we had a project with them. We traveled to their site, helped them to set up their system. So in particular, for example, they use ANSYS to model the numerical substructure because they are, it's probably industry norm and they are familiar with ANSYS modeling. So testing-wise, they use those three actuators to do DOF control to synchronize the boundary condition between the numerical and the physical substructure. So during this project, we actually developed this, we completed this user element for ANSYS to interact with the hardware. UC Berkeley started that development and eventually MTS completed that and makes it available now. So in ANSYS, you can define a user element using the provided application programming interface, the API. So this user element, you can define any type of element, numerical element yourself. You can do that. But for this specific user element, we are doing like a generic client element. So this client element is actually doing just like a communication, right? Pass the information between the command and feedback, pass it between the numerical world and the physical world. So we completed that development, and then so we went to DTU. We give the tools to them. But this is a testing we did in MTS just to prove a concept this code is working. For example, that's like just a frame structure we built, very simple. And this is a physical column we are testing in the MTS. So unfortunately, we don't have the luxury to have such a nice system like you have in your lab. So that's what we have. So we just tested that. Yeah, just give you like just a quick video. It works like your ANSYS is solving the model, right? And then in the meanwhile, it's driving this physical substructure, and the feedback goes back from the physical substructure to the numerical substructure. And this is the pseudo-dynamic as a slow hybrid simulation, right? Because ANSYS doesn't solve as fast as the real-time requirement, so it has to be slower than real-time. So that's just the results we had, X, Y, we have two actuators, right, X, Y direction. And then the hysteresis, because that column base is actually quite a nonlinear hinge in there. And we talked about this geographically distributed hybrid simulation in Professor Mahadi's beginning introduction. That's a very powerful tool, because now you can link the resources around the whole world. And you don't, any single lab doesn't have all the testing equipment you wish to have. Then if you have multiple labs, you can collaborate based on that and do this distributed hybrid simulation. And some people actually already claim they can do this distributed hybrid simulation in real time. So There are some publications already in that. And lastly, just go a little bit beyond this is like the cyber-physical system. A lot of people talk about it. National Science Foundation in the U.S. Thinks this is the future of this internet technology, and it's actually the Industry 4.0. I think that was started by Germany. So that the fundamentals of that is also all kinds of cyber-physical system. So essentially, it's just you have a lot of computational element, control, and communication all happens with our information technology. Then you have a lot of physical system, right? Like our loading system and the specimen and everything. And you combine this information technology with the physical system, and especially you make them not talk. Right? They talk to each other globally, like the distributed hybrid simulation system. That's a very good example. It's one type of a cyber-physical system. Of course, this CPS is so wide. Like Professor Masalam also said, like the daylighting control system, whatever system containing computational element and the physical element and the control action in between them, it's categorized as one type of cyber-physical system. So in our application, in the structures, at least, you have the structure, smart structures lab at the Swinburne University. So, anything smart, you can think about it as a kind of cyber-physical, because now you have a lot of things. You have structure engineering, you need to know computational mechanics, you need to know control, right? Because you need to drive the physical system, you have to know the control. You have the real-time computing, because those things all need to be embedded system, all kinds of dynamics from sensors or actuators, all kinds of modeling tools. So it's just really very large and vast concept. But I think that's something we are catching the trend. So in conclusion, we have a lot of tools we can offer to you. For example, the calculation editor help you to do either regular testing or hybrid testing. And BOF control software is a really, really advanced technique. It's very useful too if you are coming out with a very spatially distributed, like spatial configuration of a testing rig. And then hybrid simulation, we integrated 3C, computing, control, and communication, integrate all those techniques with a more realistic and affordable structure analysis. And then, again, this hybrid simulation system is just one type of CPS. And, that's just, the end of my talk. If you have any questions.
So
Yes?
just one. We showed in there this Pro station builder, where you say you've got 4 degrees of freedom or 6 or whatever on your actuation system, doing the calculations to do the transformation from physical space to a global space or global coordinates.
Yeah.
Is there also a tool there that lets you drive the rig or facility that way? Say you want to drive a rig in here or roll pitch or
Yes.
your whatever. Instead of having your 4 actuators, you've got a control system that will say run that channel.
Yes. Yeah. That's actually, I think that's exactly the invention of this tool. First place is like if you want to control, that global degree freedom, but instead you don't want to worry about how those signals are passed into each single actuator, then you use that and then it will do that for the device.
Is that a standard feature of this RTC Pro or is it a hybrid software?
The calculation editor is part of the 793 software. And the DOF is now also available in 793. It's a separate module. So the hybrid simulation is just kind of like one layer above it, utilizing the existing tool.
Thank you.
Okay.